All right, we begin. All right, what I would like to start with, what I want to talk about today is this thing called implicit differentiation. It's a bad marker. Implicit differentiation. Well, I think you have heard of this term already, maybe, because I have been using it. And that is because we have been doing it for the past week or so. And so, all right, so what is it? Well, best to just start with an example. This is not, best to just start with an example. This is not a very theoretical topic. It's more of like a kind of a practical thing. So, all right, what we have done up until this point is we have learned how to take the derivative of every function. And basically now, we can take the derivative of anything. Like, I don't think there is a differentiable function that you have heard of, maybe not counting Gabe, which we do not know how to take the derivative of at this point. That's like it's like a triple negative. Basically, we can differentiate everything now. But what I'm also interested in is something of an expansion of the concept of derivative to deal not just with functions, but with curves more generally. All right, let's just start with an example. Here is my example. X squared plus y squared equals 25. I begin with this example because it is a well-known algebraic object, or maybe geometric object. What is this? It is a circle. Okay. So here is a circle. And yeah. Okay. It's a circle with radius 5. All right. Well, what I would like to do now, is I would like to know what the slope of the line is to this curve. And what I'm gonna, let's see, what's the best way to introduce this topic? I'm not sure. So what we're gonna do is I can take this curve and I can just differentiate both sides with respect to x. Let's just do that. So I get x squared plus y squared equals 25. And now I'm going to take the derivative with respect to x of both sides of this equation, whatever that means. What did I get on the right-hand side? 0. What do I get on the left-hand side? Well, this is a little bit tricky. So okay, we can maybe split this up into two. Well, maybe it's not tricky. So this is really like two separate problems. What is the derivative with respect to x of x squared, and what is the derivative with respect to x of y squared? Well, okay, what's this? 2x. This is 2x. And then what's this?
2y times 2y.
Yeah, okay, so since we've been doing this, you guys are kind of like, yeah, no big deal. This is y squared, but since we're differentiating with respect to x, then the derivative of something squared is 2 something back inside for the derivative of the something. All right, so this is kind of weird, and what we can do, well, okay, I'll pause for a second. The reason why this is called implicit differentiation is because what we have here is actually not really a function. This is a relationship between x and y. It's the circle relationship. But in certain cases, I could, if I wanted to, solve for y. And if I try to solve for y, I get that y is like, the square root of 25 minus x squared. And there's like a plus minus kind of situation going on, right? So y is negative root 25 minus x squared. And so since it is possible, at least in this case, easily, to express y as a function of x, what that sort of means is that in place of this y squared here, we could actually substitute this entire expression. But like we sort of don't want to do that because it's really like annoying and obnoxious, and the algebra is difficult. But what we say here is that this what's it called? This equation implicitly defines y as a function of x. All right, this is like not really important. Exactly. But the idea here is that via the chain rule, I can, via the chain rule, I can come up with a formula for dy dx easily without having to deal with these kind of like disgusting representations. Okay, so solve for dy dx. What do we get?
Negative x over y.
Yeah, I mean we can kind of like move one of these or move that guy over, I guess, and divide by 2. So I get y dy dx equals negative x, and then we just divide. Okay. So what does this even mean? This is a very strange kind of formula I have here. This tells me that, well, what does this tell me? You tell me. Dan.
I mean, it kind of makes sense, right? Because if you think of like what the tangent line is at a point, like if you take the radius from like take the radius of a circle, it's like the slope, and then if you use like to find the perpendicular of like the other thing, you just like flip it and then put the negative sign from it.
Yeah, he's saying a bunch of good things. So first of all, but let's even just discuss like what is even the meaning of dy dx in this case. I mean, we have been using the expression dy dx to just refer to the derivative, right? But is this the derivative anymore? It's kind of like not really anymore. It's like, yeah.
I mean, it's like the slope of any line tangent to.
Yeah, I guess maybe this is not that big of a deal. It's like the slope of the tangent line, right? It's the way, and this is kind of the beauty of the Leibniz notation. This dy dx kind of means for us, it's the rate of change of y with respect to x. In other words, it's telling me for a particular ordered pair x comma y, how fast the y changes with respect to x. Okay, let's pick a point on this circle with nice numbers. Like 3, 4. Is that all right with you? Sure. Good. Let's do that one. So let's do. So we go up over here. 3, 4 is like up here. So. Okay. So there is 3, 4. And if I draw the tangent line to this circle at 3, 4, then it certainly has a tangent line, and the slope of this line is something that I might definitely be interested in. All right, well, what Daniel Chen was saying is, I don't need calculus actually to do this problem at all. This is just like a coordinate geometry problem. Why is this a coordinate geometry problem? You said it, but maybe you were listening, maybe you weren't. Figure out the slope of that line using no calculus, using just common sense Maya.
The slope of the radius is perpendicular to these two.
Yeah, fact about circles. A tangent line to a circle is perpendicular to the radius drawn to the point of tangency. And if that's 3, 4, then I'm going over 3 and up 4. So what is the slope of that line, or that segment? 4 thirds. And you proved, hopefully in pre-calc A or maybe in some coordinate geometry class, that if 2 lines are perpendicular, then their slopes are negative reciprocals, right? So if this is the point 3, 4, I go up 4 over 3. The slope of that line is 4 thirds, so the slope of this tangent line must then be negative 3 fourths. Agree? Okay. So all right, so all of that is like kind of pretty easy and not even really calculus. And let's just note that this formula better give us the same thing. So let's try it out. In fact, that's what this formula is. This formula is a formula which is prepared to tell me what the slope is for a particular ordered pair. In other words, it's like a kind of a function which takes 2 points as inputs. And so let's plug into this point 3, 4. This is sort of the notation for this is dy dx evaluated at the point 3, 4. Well, yeah, it just works, right? Bam. All right. So this calculus mumbo jumbo matches up with kind of what we knew the answer to be already, which makes this example sort of satisfying, I suppose. But what is this really saying? And I guess I kind of already said this, but I'll just repeat it one more time. What this is really saying is, or maybe this is the statement we should really look at. What this is saying is, when you are at the point 3, 4 on this circle, the instantaneous rate of change of y with respect to x is negative 3 fourths. So that when you are at this point, the rate at which y changes when x changes a little bit is negative 3 fourths, which is kind of like exactly what the slope is, right? the slope tells you if you change x a little bit, what happens to y? And the answer is, if you move over 1, then y will go down by negative 3/4 near that point. All right, that's kind of like all I have to say about that. Thoughts, comments, questions? Okay, good. Let's do a little, I'm going to come back to this problem in a minute, but before I do that, let's do a little thing, because it's kind of fun. Oh, fun, it's an exaggeration. Well, maybe you might even call it a lie. So implicit differentiation is this tool for which we can now find basically the slopes of tangent lines to arbitrary curves.
This looks like one of those things where you were in like second grade or something. It's like this one's like, how big is the area of this? Yeah. One of those.
So, coolest thing ever. This is, by the way, implicit differentiation worksheet. Looks like this. So x cubed minus xy plus y squared equals 4. Never mind how I graphed this answer. I used a computer. This is this curve, which is pretty awesome and exciting. What I would like you to do is, using implicit differentiation, come up with a formula for the slope of the tangent line to the curve at a given point. You guys know what to do? Work together, copy off the person who looks smart as they Oh, you turn the camera. Cool, thank you. Oh, we need to close this. The thing to do is to differentiate both sides.
It's y.
Yeah, so you guys got you're like done right. Alright, and you can, normally I would skip this step, but I'm just being, a teacher and stuff. So when I differentiate the left side with respect to x, it's really 3 separate problems, right? What's the derivative of x cubed, what's the derivative of xy, and what's the derivative of y squared? Do you want another minute, or do you want me to do it? Just don't pull stupid. Alright, you guys look mostly done, so I'll just keep going. So what is the derivative of x cubed? Well, that's just 3x squared. What is the derivative of xy? Well, careful. To take the derivative of xy, I need to use the product rule, right? So this is going to be minus whatever I get when I differentiate x times y. Well, okay, I use the product rule. Derivative of the first, derivative with respect to x is just 1 times the second, so that's a y, plus the first times the derivative of the second, which is dy dx. Is this what you guys did? It's kind of like no big deal, right? Yeah. And then what's the derivative with respect to x of y squared? Well, we've seen that already. Derivative of y to the something is 2y back inside for the derivative of the something. So now it's just a matter of doing a little bit of algebra. It's 3x squared minus y minus x dy dx plus 2y dy dx. And so you just solve for dy dx by like factoring and crap like that.
Y plus dy dx.
So I get that dy dx, what is that? 2y minus x is y minus 3x squared. So hopefully if you did it right, you got y minus 3x squared over 2y minus x. Raise your hand if you got that. Alright, enough people that I am satisfied. Okay, and just to give this some kind of sense of some concreteness or something like that, we can differentiate, we can compute the derivative at the point 0, 2. What is the derivative at the point 0, 2? Plug in 0 for x and 2 for y. What do you get? What do you guys get? 1/2. Yeah. Does it look like? Okay, I'm not going to draw the curve, but does it look like on your paper that the slope of the tangent line at the point 0, 2 is 1/2? It sure should look like it. Yeah. And now I can ask all kinds of advanced questions. Kaden, I can ask advanced questions like, where, if ever, is there a horizontal tangent? Where is there a horizontal tangent line? This problem might not be easy to solve, but just let's talk it out. Yeah.
When the top is 0.
Yeah, it's just when the derivative is 0, right? So this is there's going to be a horizontal tangent whenever basically y equals 3x squared, pretty much, right? And how would you actually find those points specifically? Plug in 3x squared for y, he says, right? So we would take the equation, which is x cubed minus x times 3x squared plus 3x squared equals 4. Are you guys following this? I just took, because Dan Jacobson answered the question when there's going to be a horizontal tangent. The answer is there's going to be a horizontal tangent whenever this numerator is 0. That happens whenever y equals 3x squared. So to find the actual points, you just set y equal to 3x squared in the equation. And what we're going to get is, okay, I didn't actually work this problem out in advance to work out or anything. Or does it work out? Wait, kind of does work out a little bit, doesn't it? No, it doesn't. This is like x cubed minus 3x cubed plus 9x to the 4th equals 4. Okay, I don't really feel like solving that equation, so I'm going to write no for now. But looking at the graph, there do appear to be some places where the tangent is horizontal. When will there be a vertical tangent? Yeah, vertical tangent when the denominator is going to 0, right? So when basically there'll be a vertical tangent when the slope of the tangent line is like more or less infinity, which happens when this bottom is going to 0. So that's going to be whenever x equals 2y. And perhaps I could solve for that. All right, you guys get the hang of this? All right, good. Back over here, now I'm going to take it to one more level. So to take it to one more level, what I'm now going to ask for is not just the slope of the tangent line, but the rate of change of the slope of the tangent line. In other words, what I want, never mind why I want this, I just do. I want to know at what rate is the slope of the tangent line changing with respect to x. Right. Even understanding what this means is kind of a strange and bizarre activity. A lot of teachers don't even talk about what it means, they just say do it. But essentially what we're doing is we're taking the derivative of the derivative. It's essentially just the second derivative, but it's the second derivative with respect to x. So it's the rate of change of the slope of the tangent line. And let's just actually like talk it out qualitatively for a moment before we do the algebra. Here I am at the point 3,4. The slope is negative here, right? How is the slope changing? What is the rate of change of the slope of the tangent line here? Positive or negative? Is the slope getting bigger or is the slope getting smaller? Yeah, the slope is getting smaller, right? Because, well, actually, it's a little bit of a vague question because it's getting smaller depending on which like direction you move or something like that, right? But what we're asking for how it changes with respect to a small change in x. And by that we mean a positive change. So the question I'm really answering right now is, if x moves over a tiny bit in a positive direction, then how does that affect the slope of the tangent line? And I think the answer is the slope of the tangent line becomes more negative. And so we should expect that the second derivative to be negative here. You guys with me? I think we have just enough time to actually do it. By the way, warning, there is a somewhat annoying and obnoxious notation, which is like very unpopular among teenagers, but just nonetheless, it's like a thing. People see this d dx and this dy dx, and they just turn this into, for shorthand, d squared y dx squared. Yeah, Arch, have you ever anything to say about that? It's just like there's no deep meaning behind that, right? It's just some annoying thing. Yeah. Do not look for deep meaning in this. It's literally just a shorthand that you have to memorize. It means this. So if you don't like this, and you probably don't, you never have to use it. You just have to recognize that that's what it means. It's just shorthand. Okay, so the warning is, don't freak out. Too late. Okay, so let's do it. Let's differentiate with respect to x, dy dx. Well, fortunately, I already know what dy dx is, right? It's this. So the derivative with respect to x of dy dx is just the derivative with respect to x of negative x over y. How can we do that? We use the quotient rule. Yeah. So let's do it. The quotient rule says it's the derivative of the top, so that's -1, times the bottom minus the top, which is -x, times the derivative of the bottom. But what is the derivative of the bottom? dy dx. All over y squared. Am I going too fast or are we cool? Okay, good, we have a minute left, so I have to go fast. But look, I actually know what dy dx is. What is dy dx?
Negative x over y.
It's negative x over y. So actually, I can write this as negative y plus x times, and in place of dy dx, I just put negative x over y. All of that is over y squared. Can you clean that up a little bit? Do a little bit of algebra 2. What do you end up with? I get negative y squared minus x squared all over y cubed. Is that what you have?
Yes.
Yeah, and then there's a cool thing you can do here, by the way. Does anyone see it? No, simpler than that. Factor out a negative. This happens kind of a lot in this situation. What is x squared plus y squared?
It's 25.
Oh, it's 25. Yeah. So the actual final answer is that. This is a formula which it turns out depends on y only, which will predict the rate at which the slope of the tangent line is changing. Exactly. So let's see if this actually makes any sense. For example, when I am up here, my slope is 0. What does it say, and what is y at this point? Y is 5, right? So what is the rate at which the slope of the tangent line is changing at this point? -1/5. Do you agree? if you plug in y equals 5. So that means the slope is changing not very fast. But by the time I get really close to 5, 0, what is that formula telling me?
Good afternoon.
Yeah, it's like
The
almost
Glasgow
negative
team
infinity,
will
which
be
is
leaving
saying
on the
that the
bus
slope is changing
directly
from like
outside the
negative
main
10
line.
to like negative infinity.
you.
All right. The more you think about it, the more it makes sense, but it's like a little bit difficult. Good job, class. That was a thing. That will be some homework on that thing. And